Hello. This video is about absolute value equations and inequalities and how to solve them. So first, let's talk about what absolute value is and what it means. We can think of absolute value as the distance from zero on a number line. For example, the number 4 is 4 units from zero. So its absolute value is 4. Negative 4 is also 4 units from zero, but in the other direction. Its absolute value is also 4. The direction doesn't matter. The absolute value is just how far away is this number from zero on the number line. So we can take some simple examples. And the notation, first of all, is like this. We put the number inside 2 vertical lines, like that, and we read this as the absolute value of n, or whatever is inside there. Could be a number, could be an expression, as we'll see later. So we read that, the absolute value of n. So the absolute value of 3 is 3, because 3 is 3 units from 0. But the absolute value of negative 3 is also 3. Negative 3 is also 3 units away from 0, but in the other direction. But the direction doesn't matter. So the absolute value of 1 is 1, it's 1 unit from 0, and the absolute value of negative 1 is also 1, it's 1 unit from 0. And 0 is 0 units away from itself. So the absolute value of 0 is 0. But it's important to remember that we're not only talking about integers, we're also talking about any real number here. So all the numbers in between the integers as well. So we can take the absolute value of a decimal, the absolute value of 2.5 is 2.5, and the absolute value of negative 2.5 is also 2.5. So the absolute value of 2.5 equals the absolute value of negative 2.5, and they both equal 2.5. So right here, between 2 and 3, right in the middle, that's 2.5, and it's 2.5 units away from 0. And negative 2.5 here between 2 and negative 3, and that's 2.5 units away from 0 in the other direction. Similarly with fractions, the absolute value of 7/8 is 7/8, and the absolute value of negative 7/8 is also 7/8. So it's the distance from 0. And of course you can just simply think of it as the absolute value of a number is the number when it's positive, or when it's negative it's the opposite. So it's always the positive version of that number. So let's look at the definition. Basically what we've just said, but we can write it down in a formal mathematical way. So the absolute value n is equal to n, it's equal to that number itself when it's positive. Like here, the absolute value of 3 is 3. 3 is positive, and so the absolute value of n is n. And that's the case here, where we write if n is greater than or equal to 0. So if n is positive or 0, then the absolute value is simply the number. So when it's 1, it's 1. When it's 10, it's 10. When it's 142.7, it's 142.7. But what happens if the number is less than 0 here. If n is less than 0, so if it's negative, then the absolute value of the number is the negative of the number. This might be a little bit confusing, seem a little counterintuitive at first maybe, but what this is saying is that if the number inside here, if n is already negative, like with -3, if you're starting with a negative number inside there, then what's the absolute value? It's the negative of that number, or the opposite, you might say. So the number inside here is -3. So what's the absolute value? It's the negative of this number, which means the positive. This is the formal definition for absolute values of real numbers. So let's look at an example with an equation. The absolute value of 6, the absolute value x equals 6. So to solve this equation, we have to think of what numbers would satisfy this, what numbers have an absolute value of 6. And there are two numbers that have an absolute value of 6. So the absolute value of 6 is 6, and the absolute value of -6 is also 6. So these two numbers satisfy this equation. So at this point, with an equation like this, we don't do any computation or algebraic manipulation. We just think of what numbers would work, and we know that it's 6 and -6. So there's two solutions to an absolute value equation here, a linear equation. Now here, we make it a little bit more complicated. Here we have not just a number and not just a variable, but an expression. We have the absolute value of this expression, x plus 1. So the absolute value of this expression is 6. Then similar to this one, we can conclude that what's inside here, this x plus 1, this expression must equal 6 or -6, because those are the numbers that have an absolute value of 6. So what's inside x plus 1 is either 6 or it equals -6. So there are two possibilities again, but we're not quite finished. Here we were finished because it was simply x inside. Now we have to solve, and when we solve this, we end up with x equals 5 or x equals -7. And we can check just simply substituting here. If x is 5, then we get 5 plus 1 is 6, and the absolute value of that 6 is 6. And we check -7. -7 for x, -7 plus 1 is -6, and then the absolute value of -6 is 6. So that works as well. Okay, now let's move on to something a little bit more complicated than this one. Okay. So now we have, again, a linear equation with absolute value, but it's just a little bit more complicated than the last one. The equation is this: 3 times the absolute value of 2x minus 7 plus 6 equals 21. And you can think of it, maybe if you haven't seen equations like this before, maybe you've seen equations where you have an expression in parentheses, like 3 and then in parentheses 2x minus 7. So it's a similar structure to that. But with parentheses you can distribute, and with absolute value you can't. That doesn't work. So we have 3 times this expression plus 6 equals 21. And I put another equation here just to kind of parallel this one, if it helps. Here we have simply 3 times x plus 6 equals 21. And maybe you know how to solve, hopefully. If you're learning about absolute value equations, hopefully you can solve this type of equation. And here the x is the variable. And in this equation on the left, instead of simply x, we have a more complicated expression. But it's the same structure. It's 3 times something plus 6 equals 21. So we think of this absolute value expression like a variable that we have to isolate. Here what we would do first is subtract 6 from both sides. And so here we're going to do the same thing. We're going to subtract 6 from both sides. And we get 3x equals 15. And I didn't write the minus 6, but that's what we're doing essentially. And here we subtract 6 from both sides. And we get 3 times this expression equals 15. So we have the same structure, but instead of x, we have this more complicated expression. And the next step is the same in both cases. Here we would divide by 3 on both sides and get x equals 5. Here also, we divide by 3 on both sides, but instead of x, we'll have this expression, 2x minus 7 inside the absolute value equals 5. So we divide by 3 on both sides, divide by 3 on both sides. So here we're finished. We've found x. Here we've found what this expression equals. This expression of absolute value of 2x minus 7 equals 5. And now we have an equation similar to before. So we have to keep going here. And the way we proceed is we have to realize that the expression inside has to equal 5 or negative 5. Those are the only things that have an absolute value of 5. So 2x minus 7 inside the absolute value must be either 5 or negative 5. And we create now those two equations. So 2x minus 7 equals 5, that's one possibility, or 2x minus 7 equals negative 5. And then we just solve these two equations separately. So here we get x equals 6, and here we get x equals 1. And we could check these answers in our original equation. If x equals 6, then here we get 2 times 6, 12, minus 7 is 5. Absolute value of 5 is 5. 3 times 5 is 15, plus 6 equals 21. We can check 1, put 1 in for x. 2 times 1 is 2. 2 minus 7 is negative 5. But then the absolute value of negative 5 is 5. 3 times 5 is 15, plus 6 is 21. So we can have these linear expressions inside the absolute value, and we can do operations on this absolute value expression. We can multiply it by something, we can add something to it, etc. Now let's talk about absolute value inequalities. So here we have the absolute value x is greater than or equal to 2. So we have the or equal to. So let's start with that. What has an absolute value equal to 2? It's going to be 2 and negative 2. What has an absolute value greater than 2? Well, we can think about it in terms of distance on the number line, or we can just think about it in terms of the definition and what we know. So we know, for example, that 3 has an absolute value of 3, which is greater than 2. So 3 would satisfy this, and similarly 4, 5, 6, they all have absolute values greater than 2. And also to the left of -2, -3 has an absolute value of 3, which is greater than 2. -4 has an absolute value of 4, which is greater than 2. So 2 and -2 have absolute values of 2 that equal 2. So these are solutions to this inequality, 2 and -2. And anything to the right of 2 is going to have an absolute value greater than 2. And anything to the left of -2 will have an absolute value greater than 2 as well. And we can think of it in terms of the distance on the number line. This means that the distance from 0 of this number is greater than 2. So this number is greater than, or more than 2 units away from 0. So it's got to be more than 2 units away from 0 to the right, or more than 2 units away from 0 to the left. And so now we can represent the solution a couple of ways. The solution is I would say the most concise, the best representation is simply this. The solution to this inequality is x is greater than or equal to 2, or x is less than or equal to -2. And we can also represent this on the number line. And one way to do that is like this. We draw the solution, and we have 2, so we could do it like this. We could do it above 2. And I colored in the dot rather than making it an open circle to show that 2 is itself a solution. If it wasn't a solution, if it was strictly greater than, for example, 2 would not be a solution, and I would make it an open circle, but we'll do an example like that after. And here, anything to the right of 2 has an absolute value greater than 2. So I draw that. Similarly, -2 is a solution. Color it in. And anything to the left of -2 is a solution as well. So this is one way to represent visually the solution to this inequality. And it's important to be aware, to mention, that we're not only talking about the integers. We're not only talking about 3 and 4 and 5 over here, and not only the numbers that go after that. We're also talking about all of the numbers, the real numbers in between the integers. So 2.5 is a solution, and -2.1, and 2.0034, all of those numbers are solutions as well. So with the absolute value equation, remember we got 2 solutions. And here with the inequality, we get, well, not 2 solutions, we get infinitely many solutions, all of these numbers, but we get 2 parts to the solution. If it wasn't an absolute value, we would only get 1 part. Let's look at now less than. So here we have the absolute value of x is less than 2, and it's not less than or equal to, it's strictly less than. So it's going to be here 2 is not a solution, -2 is not a solution. But we're going to use those as our reference points. So we have to decide what has an absolute value less than 2. Well, 1, for example. -1 also has an absolute value of 1, which is less than 2. And all of the numbers in between, 1.5, 0.2, and -0.6, all of those numbers in between here. And visually, I think it's important to think about it sort of visually in terms of distance on the number line. This inequality is saying the absolute value of x is less than 2. So the distance away from 0 is less than 2. X is less than 2 units from 0. So it's up to, and not including, but up to 2 units from 0. All of these numbers are less than 2 units from 0 and not 2. So I'm going to draw this more or less open circle. And to the left, of course, we have these numbers are less than 2 units from 0. Negative 2 is exactly 2 units from 0. So 2 and negative 2 again do not satisfy this inequality. But all of these numbers between satisfy this inequality. And I did this 2 different ways here, you can see. One way is to draw the solution above the number line, or you could do it below, I suppose, as separate lines, arrays. Or the other way is to do it right on the number line and to highlight or darken the number line where the solution is. Either way, I've seen both, so there isn't one that's correct. Either one works. But you can see here, when we have an absolute value is greater than something, we're talking about distances greater than something, and the solution will go to the right and to the left. But when the absolute value is less than something, we're saying the distance is limited. It's up to a certain distance. And so we have this solution in between values. And here's how we write this solution for the second inequality. X is greater than negative 2, and x is less than 2. And it's very important to know when to use the word or and when to use the word and. So in the first example, there's solutions over here and there's solutions over here. So x could be, for example, 4, or x could be negative 7. It could be either these numbers or these numbers. But in the second example, we're saying that the solution, the values for x, are between 2 and negative 2. So they are the numbers which are greater than negative 2 and less than negative 2. So greater than negative 2 would include everything to the right. Less than 2 would include everything over here to the left. But when you say and, it's got to be both. And where is it both greater than 2 and less than, greater than negative 2 and less than 2? And that's in between. So with greater than, we're going to use or, and with less than, we're going to use and in our solution, and that's why. But we'll talk a bit more about that in the next examples. And finally, we can actually express this in what's called a compound inequality. So we're basically taking these two inequalities, and since it's and, we can, in a very concise way, express it as a single compound inequality. We're basically just putting the two together. We say x is less than 2, there's x is less than 2, and at the same time, x is greater than negative 2. So you can sort of read this backwards. X is greater than negative 2, or negative 2 is less than x. It's the same thing, but when we flip it around, we can write it concisely this way. So now let's take what's inside the inequality, or what's inside the absolute value, rather, and instead of x, we'll make it an expression. So here we have x plus 5. inside the absolute value. The absolute value of x plus 5 is greater than 6, or equal to, greater than or equal to 6. So this gives us two possibilities. The thing that's inside the absolute value could be greater than or equal to 6, in other words, to the right of 6, or it could be anything to the left of negative 6, like in our example with negative 2. The absolute value is greater than 2. So the distance from 0 of this thing is either more than 2 to the right or more than 2 to the left. So here, the distance of this thing from 0 is either more than 6 to the right, so greater than 6, or more than 6 to the left, less than negative 6. And once we set up those two, we solve them separately. So here we have x is greater than or equal to 1, and here we have x is less than or equal to 11. And it's an or, so we can't combine them into one inequality. We have two parts to the solution. There are numbers over to the right and numbers over to the left. And we can put that on the number line. So we'll put 0 maybe here. And we'll put 1 here. And we'll put negative 11 over here. And so the solution, even though in the beginning we were talking about being to the right and the left of 6, this is something that maybe sometimes confuses people. This expression, the absolute value of this expression, is either to the right of 6 or to the left of negative 6. But when we solve for not the expression but x itself, we find that x could be anything greater than 1 and equal to 1 also, because greater than or equal to. Or it could be anything less than or equal to 11. And we can check. It may help to check. We put in 1 for x, and we see if we put in 1, we get 1 plus 5 is 6, and the absolute value of 6 equals 6. And it's greater than or equal to that. That is the solution. And if we put in anything bigger, we put in 2, 3, 4, we'll get numbers that work as well. Over here we can put in negative 11. Negative 11 plus 5 is negative 6. And the absolute value of negative 6 is 6, which is greater than or equal to, it's equal to 6. And if we put in values less than negative 11, negative 12, for example, we'll get negative 7. Absolute value of negative 7 is 7, which is greater than or equal to 6. So we have this solution. And now let's do one with less than or equal to inequality. So let's try this one. The absolute value of 2x plus 1 is less than or equal to 9. And maybe it'll help if I start with this. We have, let's say, 9 and negative 9, more or less the same distance. So this expression has an absolute value less than 9. Or in other words, the distance from 0, whatever this expression equals, its distance from 0 is less than 9. So the value of this expression is between 9 and negative 9. It's less than 9 up to 9 units to the right and up to 9 units to the left. But here we're talking about this expression, not x, so we'll find x after. But we know that this expression is between 9 and negative 9, and it's or equal to, so 9 and negative 9 are also possibilities for this expression. So you can remember the rules. You can remember, when it's less than, I do this, and when it's greater than, I do that. But I would suggest thinking of it conceptually always. So this expression, its absolute value is less than 9, so its distance from 0 is less than 9. So up to 9 to the right and up to 9 to the left. So we can write that this way. We can say this expression is less than or equal to 9, but it's also got to be greater than or equal to negative 9. It's got to be in between. And we can actually write it, rather than write two separate inequalities, we can write, in this case, one combined inequality. And we can solve it like we would normally solve an inequality. We would first subtract 1. And if it was a simple, single inequality, we would subtract 1 from both sides. And in this case, we can just subtract 1 from all three sides, or all three parts. And so we'll get 2x, and here we get 8, and here we get negative 10. So we subtract 1 from all three parts. And now what we would normally do, we divide by 2, and we do that in all three parts. So we get negative 5 is less than or equal to x, which is less than or equal to 4. So now we know x. We know x can be any value between negative 5 and 4, including 5 and negative 4. And so we'll graph that here. 0. And we'll do 4 here. And negative 5. So it's all the values between 4 and negative 5. And it's greater than or equal to, so these values are included, so we'll color in the circle. So again, we start out by thinking about this expression and where this expression is, what are its values, as if it was just x. And it is less than 9 units from 0 in either direction. So this expression is between negative 9 and 9. And then we solve the inequality like we would normally solve inequalities, linear inequalities. Okay, let's now, last thing, let's take a look at a quadratic inequality with absolute value. So here, we can expect, well, how many solutions can we expect? How many parts to the solution? I mentioned that with an inequality, normally a linear inequality, we get one piece. We get greater than something or less than something. But when there's absolute values involved, we get two parts. We can either get something to the right or something to the left, two parts, or we get two parts where they overlap like this. And with the equations as well. Normally in an equation we have one solution, but when there's an absolute value involved, we get two solutions. So here with a quadratic equation, we can get, well, we don't always, but we can get two solutions, maximum. So when there's an absolute value involved with a quadratic equation, we can expect that sometimes there will be up to 4 solutions. And that's what's going to happen here as well. And there could be fewer, but let's see why we get 4 solutions. So this expression, x squared plus 2x minus 4, has an absolute value less than 4. So, just like the last problem, we can say, okay, the value of this expression, just like if it was a big variable, this expression is less than 4 units from 0. So it's between 4 and negative 4 on the number line. What numbers have an absolute value less than 4? Well, 3, 2, 1, 0, negative 1, negative 2, negative 3, right? And also the decimals in between. So between negative 4 and 4, those numbers have an absolute value less than 4. So we can start by setting up this compound inequality, and this is really two separate inequalities. And in fact, in this case, we have to think of it as two separate inequalities, because how would we solve a quadratic equation or inequality? One way, normally, if we want to try to factor it, or use the quadratic formula, for example, we would set everything equal to 0. We would move everything to one side and have 0 on the other side. But we can't do that here because there's 3 parts. So if we try to get this side equal to 0, this side won't be. And if we try to get this side equal to 0, this side won't be. So in this case, we need to take this and we need to actually split it into the two separate inequalities. With the equation, it was nice and convenient. We could just add something to 3 parts and subtract something to 3 parts, or divide all 3 parts. But with a quadratic, it's not so simple. We have to break this up into 2 separate inequalities. And that's okay. So we have those 2. And we have negative 4 is less than this. And I wrote it exactly as it is. And here, our expression is less than 4. And now we can solve these. Over here, I add 4 to both sides. And I get 0 is less than x squared plus 2x. In this one, I subtract 4 from both sides to get 0 on one side. So when I subtract 4, I end up with x squared plus 2x minus 8 is less than 0. So I subtract 4 from both sides. Here I add 4 to both sides. And now I have one side equal to 0 in both cases. So at this point, we can factor. Sometimes factoring doesn't work, of course, and you have to try something else, maybe use the quadratic formula. But here we can factor. We factor this expression, we get x times x plus 2. And over here, we factor this, we get x plus 4 times x minus 2. So, what are the values of x? Now these are inequalities. We're talking about inequalities. But for the moment, let's just think about it as an equation. In other words, let's think about which values of x make this expression equal 0 here, and which values of x make this expression equal to 0. So over here, 0 and negative 2 are the solutions to make it equal 0. And in this one, negative 4 and positive 2 are the values of x that would make it equal to 0. So those are not solutions, because it's not less than or equal to. Not less than or equal to in the original equation, in the original inequality. But those are our starting points. We're going to use those points. Let's look at those points on the number line. So we have 0, negative 2, negative 4, and 2. We know these are the points that make these expressions equal to 0, and therefore those are the points that would make this original expression have an absolute value equal to 4. So what we need to do is check numbers that are in between these points. we can check, for example, we can check 1, we can check -1, we can check -3, check +3, and we can check -5. In fact, you could check any number in between there. It doesn't have to be those. And we can check at any point in the process. But just to be safe, make sure we didn't make a mistake, let's check in the original inequality. So for example, I'm going to check the value 1. I'm going to put 1 into this inequality and see what happens. So substituting 1 in for x, we get 1, 2, 1 plus 2 is 3, minus 4 is -1. Absolute value -1 is 1, and 1 is less than 4. So it's true. So when I check 1, it works, right? So this is a yes. The numbers in here, and I already know, I don't need to check, you can think about it yourself. I don't need to check any other numbers in here. Because this is one of the reference points, this is one of the points that makes it equal, and this is one of the points that makes it equal. All the points in between will either work or not work. So 1 works. Let's check -1. -1 squared is 1. This will be -2. So 1 minus 2, -3 minus 4, -7. Absolute value is 7, which is not less than 4. So the numbers in between here do not work. Let's check 3. What do we get? 9. And that's 6. And 9, 6 is 15. Minus 4 is 11. The absolute value of 11 is 11, which is not less than 4. So this is also a no over here, and that's for all the numbers to the right. Next, we'll check -3. -3, that's 9, and -6, 9, minus 6 is 3, minus 4, -1. Absolute value of -1 is 1, and 1 is less than 4, so that's true, so that works. And the last one is -5, and maybe you can see a pattern here, and in fact, we'll just double check. -5, so we get 25, that would be -10, 25 minus 10 is 15, minus 4 is 11, absolute value of 11 is 11, which is not less than 4, and so this is a no. And so we have these solutions here, it's yes. Again, these should be big open circles because those are not solutions. But only the numbers in between. This should not be highlighted. So it's these numbers and these numbers and only those numbers. So the correct way to write the formal solution is like this. X is between -4 and -2, not including 4 and -2. And x is between 0 and 2, not including 0 and 2. So they have two compound inequalities. So that's the last example I'm going to do. And I hope, of course, that was clear enough and helpful. And at the very least, relaxing. One or the other or both. If there's any part that was unclear or you have questions, please don't hesitate to post a comment or question, and I'll try to elaborate or re-explain it another way. right, thank you very much, and see you next time.